Good afternoon, everyone. I am Maria Elidayana da Silva Pereira, and I am a postdoc at the University of Michigan and a member of the Dark Energy Survey collaboration. And I will talk about the cluster cosmology analysis that we are developing for the third year of data. So it's an overview of this talk. We'll give an introduction on clusters and cosmology. Then we'll talk about the results that we got for the SY1. And finally, I will talk about the plans that we have for the SY3 and summarize this talk. So why galaxy clusters for cosmology? So galaxy clusters are the largest objects in the universe that are bound by gravity. They are also formed by dark matter, galaxies, stars, gas. So it's a very extreme environment and very useful to study astrophysics. For example, the intercluster medium, intercluster light, and galaxy evolution. But they are also very powerful cosmological probes. As I say, they are the highest density of matter in the universe. So they can give us some idea of how the structures grow in the universe. And to give an example on how sensitive galaxy clusters are to the cosmology, we can look here in this picture where we have the number of galaxy clusters as a function of a redshift, this for a given mass. And as you can see, the number, or what we call the abundance of galaxy clusters, change a lot depending on the cosmological model. In this case here, for these cosmological models, the parameter that is very sensitive to the abundance of galaxy clusters is what we call S8. S8 is a parameter that give us some idea of the clumpness of the universe. And it is a combination of the density of matter, omega matter, and the amplitude of the density fluctuations at scale of 8 megaparsecs, so what we call the sigma-8. But here's a more intuitive way to think about S8. Here we have two different universes in which they're the same. The only thing that we change is the quantity, the amount of the S8 in each one of the simulation. And the universe on the left has a value of S8 that is lower than the one in the right. And as you can see here, the universe in the left seems to be more homogeneous than the one on the right. Also, you can see here by looking to the yellow orange dots, which would be galaxy clusters, the regions where we have galaxy clusters, that the different simulations have a different quantity of galaxy clusters that are formed. So that's also something that just show clearly for us how the cosmology through this parameter S8 is sensitive to the number counts or abundance of galaxy clusters. So it's a very powerful measurements, and several surveys are trying to do this. And we can see here in this plot where we have S8, as I say, it's a combination of omega matter and sigma-8, and the measurements from different surveys. And here we have measurements from clusters in different wavelengths, from optical, SZ, and X-ray. But also we have here in red measurements from weak lensing through the cosmic shear. And as you can see, those measurements of the late universe seems to be lower than the measurements from CMB, given here by these points in magenta. And some people might think that this could be evidence for some new physics or something going on with the lambda CDM. But it is more likely that this kind of tension, not so it's not clear that's really attention, is more likely to be explained by systematics. And in the case of galaxy clusters, I can tell you in the next slides that this is related to the systematics involved in the mass estimation of the galaxy clusters. So to use clusters for cosmology, we need basically 3 ingredients. The first one, we need to identify galaxy clusters. And to do that, we use what we call the red sequence. Basically, this is the fact that the majority of galaxies that form our galaxy cluster are red elliptical galaxies. So that, and if we look to a region in the sky where we have an agglomeration of red galaxies at the same redshift, it's very likely that we are looking to a galaxy cluster. So different cluster finders use this red sequence to identify the clusters. Once we do that, we need to measure the mass of these galaxy clusters and then use this information together with the number count prediction for the number counts to get the cosmology. So, but as I highlight here, the estimation of the mass is very challenging because we cannot assess the true mass of the galaxy clusters. We need to rely on observables, some indicator for the mass, because you can just observe light, right? So we could use, for example, the number of red galaxies that we call richness, lambda, as an indicator for the mass. We could also use the stellar mass content of the galaxy clusters and the X-ray luminosity, or any other observable that we think correlates well with the total mass of the galaxy clusters. However, the clusters, they are formed mostly by dark matter. And we know that we can have a better estimate of the total mass by using the gravitational lensing effect, because this effect is sensitive to all the matter in the galaxy clusters, not only the visible, but also the dark matter. And just to remind you, in the lensing effect, we have here in this plot observer, and then some distribution of matter, which could be a galaxy or a galaxy cluster, and then background galaxies. And what happens is that the light of this background galaxy, when passed here nearby the galaxy distribution or cluster, the light is deflected. And then as a result, we see a change in the shape of this background galaxy. And this change in the shape of the background galaxy are proportional to the mass of what we call the lens, or galaxy cluster. Therefore, this is a way to have access to the mass of the galaxy clusters. However, we cannot see this effect by eye. We need to measure statistically. So what we do basically is split our cluster sample in cluster who has similar properties, for example, say same richness or same redshift, and put them all together, stack them, and to increase our weak lensing signal. So that's a way that we usually do in the cluster mass estimation with weak lensing. Then finally, what we can do is calibrate, the mass, the observable that we have, as a function of the total mass given by weak lensing. And ideally, we would have a linear relation between these two quantities, but since you do measurements, we have errors, therefore we have scatter in this relation. And also we have limitations from our sample. We cannot observe all the galaxy clusters in the sky. So there is this limitation of all detection. So at the end of the day, we need to do this kind of calibration here using this data, which is not an easy task, but we did that. And for the SY1, we use around 6,000 galaxy clusters using this redMaPPer algorithm, which is based on the red sequence. And we had measured 30 millions of shapes of background galaxies to measure our weak lensing signal. And we went to up to redshift of 0.7 for this cluster sample. And we performed these weak lensing measurements and then mass calibration as a function of richness. And this is one of the most precise results that we have here in this light blue region. And if you can compare with previous measurements, you can see how precise this mass calibration for the SY1 was. And once we perform this calibration, we can use this information together with the number counts. Number counts is simple, it's just count the number of clusters that you see in a given beings of richness and redshift. And we use these two information together to get the cosmology, right? Since number counts proportional to S8. So the result is here. In this plane, you have 𝛾8 and 𝛾₀, and the result is in gray, and we can compare with Planck in orange. And as you can see, there is a tension between these two results. This tension is up to 5 sigmas. And the reason for that was discussed in this paper here. Here's just another way to see this result in terms of S8. And the result is here in this white dashed line here, vertical line. And again, if you compare here with these green dots, the CMB, there is a clear tension between these results. And after some investigations in this paper, we conclude that it's most likely that we underestimate or are having an incomplete understanding of systematics related to the mass calibration. And this driven this offset in sigma S8. And again, it could also be systematics related to the sample of low richness cluster that we have, in which we are estimating a lower mass. Or it could also be projection effects, selection effects, or contamination related to our cluster finder. So this is all things that could play a role in this bias in our cosmological results with clusters in the SY1. So this is something that you still need to understand. But to give some idea on the different systematics involved in the mass calibration, I will just present some of them, most of them actually. The first one is what we call model bias, which is basically due to the fact that we assume the clusters to be spherical NFW profile, and they are not in reality, right? So we need to correct for this assumption. And you can use simulations to do this correction. The other effect is what we call boost factor. Basically, if you look here to this image, we have galaxy cluster and then galaxy members of this cluster. And because we have uncertainties in the photometric redshift of this galaxy, it could be that some of them leak to the sample of background galaxies. But these member galaxies, they are not lensed, they do not suffer from the lensing effect, right? Therefore, they will dilute the weak lensing signal of the background galaxies. So we need to correct and give a boost in the weak lensing signal. That's why this name is boost factor. The systematic is boost factor. The other systematic is the miscentering. This is pretty clear. It's basically due to the fact that we give wrong center for the cluster. So if you look here in this picture, if you have a cluster that you give the correct center, as here, this yellow triangle, and the other cluster, we also give the correct center. And when we combine those two by stacking, we have a nice weak lensing profile. However, if our cluster finder give the center as this green square here for this cluster and this other green square for the other cluster, when we combine them, then we have a dilution of our lensing signal. So we need to correct for miscentering. And usually we do that by measuring the fraction of miscentered clusters in a sample by using, for example, X-ray data, who has a more precise center than the optical clusters. So this is a way to correct for miscentering. And finally, I already mentioned that photometric redshifts have uncertainties. So here is just an example of photometric redshift estimation as a function of true or spectroscopic redshift. And as you can see, there is some bias, outliers. So there is a lot of things going on in here when we use photometric redshifts that we need to correct for. And the other systematics is shear bias, which basically is this fact that we have here a nice galaxy, and then we have lensing, but we observe this galaxy from a telescope here on Earth. So we have a atmosphere and the point spread function that make things blurry. And also we detect in a camera, so we have a pixelized image and you have noise. So this is the kind of image that we need to measure the shapes. Then we could imagine that there is some bias in the recover of the shape of this background galaxy. So this is something that we also need to correct for. And finally, we have triaxiality and projection effects. Triaxiality is simple. If you look here in this image, as I say, real clusters are not spherical in FW profiles. They have a potato shape, and depending on the alignment of these of the major axes of these clusters, they could be aligned to the line of sight, or could be perpendicular to the line of sight, as you can see here, and therefore this will make a change in the weak lensing signal that we recover from these clusters. And just to mention, redMaPPer has a preference to find clusters that are in this configuration here. So this is also something that we need to take into account, this selection effect. And finally, with the projection effects, is basically the fact that we have a cluster and then in the different clusters at the same line of sight. And because of the uncertainties in the membership, so some member galaxies of these clusters that are in the foreground could be identified as the cluster, as this cluster here in the background. So this change in the membership assignment of those clusters has impact on the estimation of the richness lambda. Therefore, it also impacts the mass recover. So this is also something that we need to understand and correct when doing weak lensing mass calibration with optical clusters. So as you can see, it's a lot of work to try to estimate the weak lensing mass from those galaxy clusters in our optical sample. But we are doing this. We have some papers that is just out very recently, explaining the improvements that we did for Y3 data. For example, in the redshift estimation using a new code. And we also have some improvements in the shear measurements. So if you want to see more details, look to those papers. But we also have new corrections for projection effects and triaxiality. And we're still working and trying to understand the selection effects and also the lensing signal of the low richness clusters. And once we finalize these new corrections and modeling of those systematics, we can finally get the cosmology for the SY3. And we are planning to do to get the cosmology in a slightly different way from the SY1. In this case, we will use this sample that we have now of it's a sample of 20,000 galaxy clusters. And now we have 100 millions of background galaxies to use for the lensing estimates. We still at the same redshift range of 0.7, but we use this information to get the lensing signal and the number counts. And we are not doing a mass calibration step. We are just using these two data sets all together in single likelihood, combined likelihood, in what we call full forward modeling of the number counts. And this is it's good because we will take into account the correlation between these two data sets properly. But again, we can, by doing this combination, can get the cosmology. Another improvement that we are doing this analysis is to use multi-wavelength data to understand, to put priors in the observable-mass relation, since now we are not using the doing the part of the mass calibration. You are just using the lensing signal and marginalize over the observable-mass relation. So we can use priors to do this in a better way. And we are also using information from simulations to try to understand the signal from the lensing signal from the low richness cluster sample. So this is also something that we are doing for the Y3 data. And once we have all this thing together, we finally we have our results. And we expect to have the cluster cosmology Y3 results by this fall. So stay tuned. And but besides this fiducial analysis that we will be doing by putting together lensing profiles with number counts to get the cosmology, we will also use we will have two other approaches to get the cosmology. One alternative approach is to use the number counts from YES in combination of the observable-mass relation from multi-wavelength data, for example, in this case, SSZ clusters, and using this scaling relation from SZ together with the number counts, we can constrain the cosmology. And here is the result that we had for Y1. And the results here in magenta, and if you compare with Blanco in light blue, you can see the agreement is much better now. So this is one alternative approach that we will also do for Y3. The other approach is to do the number counts from the Y3 in combination of the what we call the two-point statistics, so the clustering. And this, again, this is, we already applied this methodology in these two papers here. And the first one was applied to simulation to develop the methodology and test selection effects, for example. And here's the result in data, for cosmological results in data, using this approach. The results here in orange, and we can compare with Blanco here in magenta. So as you can see, they are in a much better agreement now. So this is also another approach that we will be doing for Y3. The only disadvantage of this methodology is that we can just go to higher radial scales. And for Y3, we are trying to push this down for lower radial scales to increase the constraining power from this technique. And to summarize, cluster cosmology is hard. Measuring the mass of clusters is even harder. So currently, we have mass estimation, mass calibration that has 5% uncertainties. But we already have seen some problems with that. And besides of solving this problem, we still need to get to the 1% level for future surveys. For example, Rubin Observatory, Euclid, So we need to fix the systematics and need to improve. And we also have seen some this offset in the cosmological results by using the clusters year 1 data. And we have some insights on what could be the reason for that. It could be the lensing signal of the low richness clusters that we are not modeling properly. It could be selection effects, contamination for cluster finders. It could also be related to triaxiality and projection effects that we did not properly correct. It could be a combination of all of those. So this is something that we're still investigating. And once we finally do that, we can get the cosmology. And as I mentioned to you, we have 3 approaches for the SY3. The first one is to do a full forward modeling of the lensing profiles with the n+𝛾T. And the other approach is to use n+𝛾T with multiwavelength data, for example, SC observable-mass relations. And finally, we will use n+𝛾T together with 2-point statistics from clusters. And hopefully we have exciting results to present by this fall. So stay tuned. And thank you to give me this opportunity to talk in this event. And thank you for your attention. And I think if you have any questions, you can just contact me. So thank you.